Hi everyone, here we are going to see about the Unit 4 continuation. So that is the rounding process. So rounding, we have already seen about the rounding process. Now here we are going to see about the rounding will be having that when we get the binary numbers, the finite word size means we have to round the value to particular points. Truncation means that is we have to truncate the values. That means if you are having the values in the higher bit means we have to truncate the length of the bit to smaller. So likewise we have to truncated the values. Then we have to take the truncated error for 2's complement form and then found out the round off error values. So quantization noise. So here in this quantization noise we are going to derive the expressions for the signal to quantization noise ratio, and also we are going to know about what is quantization noise and what are the expressions are required for the quantization noise power. So here is that when we are passing the x of t as the input, it will be passed into the sampler, and the sampler will be convert the get the particular time level, that is t is equal to nt, and then change it to the x of n value. After that the x of n value will be given to the quantizer and then passed to the xq of n. Okay. So the analog signal which will be converted into the digital signal by ADC method only. So the first signal x of t is sampled at the regular intervals of t is equal to nt. So here where n is equal to 0, 1, 2 etc. have been taken. So we have to create the sequence x of n. So this should be done by the sampler. Next, numeric equivalent of each sample x of n is expressed by finite number of bits and it is given to the sequence of xq of n. So the different signals E of n is equal to xq of n minus x of n, which is called as a quantization noise or analog to digital conversion noise. So let us assume a sinusoidal signal varying between +1 and -1 having a dynamic range tube. So the ADC will employ b+1 bits which will include the sign bit. So in this case the number of the levels available for quantizing the x of n is 2 to the power of b+1. So the intervals between the successive level is q is equal to 2 by 2 to the power of b+1, that is equal to 2 to the power of minus b, where q is the quantization step size and b is the 3 bits and q is the 2 to the power of minus 3 means 0.125. Next is the quantization noise power. So there is a x of t sampler, then we get the x of n and then we go to the quantizer. After that we will receive the xq of n and then it should be enters into the encoder part. So probability density function for a round off error in analog to digital conversion is shown in the figures. So if we have to round off the values means it is used for quantization. So that is bounded by minus q by 2 less than or equal to e to the e of n less than or equal to q by 2. So then the error will be lies between minus q by 2 to q by 2. So with the equal probability where the q will be the quantization step size. So the properties of the analog to digital conversion error is E of n, and the error sequence E of n is a sample sequence of stationary random process. So the error sequence is uncorrelated with x of n and the other signals in the systems. So this error will be having the white noise process with uniform amplitude probability distribution over the range of quantization error. So the variance of E of n is given by sigma E squared is equal to E of E squared of n minus E squared of E of n. So that is E of E squared of n, that is average of E squared of n, and E of n is equal to mean value of E of n. So for rounding E of n lies between minus q by 2 and q by 2 with the equal probability. So there is E of E squared of n is equal to summation integral minus infinity to infinity E squared of n P of E into dE. So P of E is equal to 1 by q and q minus q by 2 less than or equal to E of n less than or equal to q by 2. So substituting 3 in 2 means we get E of e squared of n is equal to integral minus q by 2 to q by 2 e squared of n into 1 by q into dE. So that is e of e squared of n is equal to 1 by q integral minus q by 2 to q by 2 e squared of n into dE. So that is e of n is equal to 0. So e squared of n is equal to 0. So substituting the 4 and 5 in 1 means that is a sigma e squared is equal to 1 by q integral minus q by 2 to q by 2 e squared of n into dE minus 0. So that is 1 by q into e cube by 3 the whole power q by 2 to minus q by 2. So 1 by 3q into q by 2 minus q by 2. So 1 by 3q cube by 8 minus q cube by 8. So that is 1 by 3q q cube by 8 plus q cube by 8. So that is 1 by 3q into 2q cube by 8. So that is epsilon e squared is equal to q squared by 12. So 1 by 2b is equal to 2 power minus b, that is equal to q. Epsilon e squared is equal to 2 power minus b by 12. So epsilon e squared is equal to 2 to the power minus 2b by 12 we will get. So there is the equation 8 will be known as the steady state noise power, which will be due to the input quantization. So there is q is equal to r by 2 to the power of b in 2's complement representation, and q is equal to r by 2 to the power of b minus 1. That is in sign magnitude or 1's complement representation. R is the range of the analog signal to the quantization. Next is the steady state output noise. So that is x of t, sampler, x of n, quantizer, xq of n, encoder, processor, output noise power. So after the quantization level, we have a noise power, that is a sigma e squared as a input noise power. So the output noise power of the system is given by sigma 0 squared is equal to sigma e squared into summation n equal to 0 to infinity h squared n of n. So that is x of n is given, e of n, xq of n, h of n, y of n. So h of n means impulse response of the system. Let error e of n be output noise power due to the quantization. So e of n is equal to e of n into h of n. So that is summation k equal to 0 to infinity h of n into e of n minus k. So the variance of the error e of n is called output noise power. So that is sigma e squared. By using the Parseval's theorem, sigma e naught squared is equal to sigma e squared into summation n equal to 0 to infinity h squared of n. So that is sigma e squared 1 by 2 pi a in so that is the variance of the error e of n is called the e of n be output noise power due to the quantization. So e of n is equal to e of n into h of n. So that is summation k equal to 0 to infinity h of n e of n minus k. So the variance of the error e of n is called as output noise power and sigma e squared. By using the Parseval's theorem, then sigma e naught squared is equal to sigma e squared into summation n equal to 0 to infinity h squared of n. So sigma e squared is into 1 by 2 pi f integral h of z into h of z inverse into dz by z. So by the closed contour integration is evaluated using the method of a residue by taking only the poles that lie inside the unit circle. So the z transform of h of n, h of z is equal to summation n equal to 0 to infinity h of n z power minus n. So the z transform of h squared of n is equal to z h squared of n. So that is equal to summation n equal to 0 to infinity h squared of n is z power minus n. So summation n equal to 0 to infinity h of n is z power minus n. So we have to take the inverse z transform. So that is h of n is equal to 1 by 2 pi f integral h of z into z power n minus 1 into dz. So substitute this 11th equation in the 10th equation. So we will get summation n equal to 0 to infinity h squared of n z power minus n. So that is equal to summation n equal to 0 to infinity 1 by 2 pi f integral closed integral h of z into z power n minus 1 into dz h of n z power minus n. So that is we will get a summation n equal to 0 to infinity h squared of n is equal to 1 by 2 pi f integral h of z summation n equal to 0 to infinity h of n into z power minus 1 dz. So we will get a summation n equal to 0 to infinity h squared of n into that is equal to 1 by 2 pi f close integral h of z inverse into d z by d z. So substituting this 12th equation in 9th means we will get sigma e naught squared is equal to sigma e squared into 1 by 2 pi f integral h of z inverse into z inverse dz. So let me. So the output signal of the analog to digital converter is passed through the first order low pass filter with the transfer function given by h of z is 1 minus a into z by z minus a for 0 less than or less than a less than 1. Find the steady state output noise power due to the quantization at the output of the digital filter. So here is the solution, that is sigma e squared is equal to sigma e squared into 1 by 2 pi f closed integral h of z inverse into z inverse dz. So given value is h of z is equal to 1 minus a into z by z minus a. So that is h of z inverse is equal to 1 minus a into z inverse by z inverse minus a. So substituting these values in equation 1, we have sigma e squared is equal to sigma e squared by 2 pi fc closed integral 1 minus a into z by z minus a into 1 minus a z inverse by z inverse minus a into z inverse into dz. So we will get sigma e squared by 2 pi fc closed integral that is 1 minus a the whole squared by z minus a into dz by z inverse minus a into z inverse. So that will be known as sigma e square into residue of h of z inverse at z is equal to a plus residue of h of z inverse a at z is equal to 1 by a. So that is z minus a into 1 minus a squared z inverse by z minus a into z inverse minus a plus 0. So that is 1 minus a squared by z inverse minus a, that is equal to sigma e squared into 1 minus a by 1 plus a. So where q is sigma e squared is equal to 2 to the power of minus 2b by 1 by 12. So this will be the answer. Next question is find the steady state variance of the noise in the output due to the quantization of the input for first order filters. So there is y of is equal to a y of n minus 1 plus x of n. So the impulse response for the above filter is given by h of n is equal to a power n into u of n. So that is sigma e squared is equal to sigma e squared into summation k equal to 0 to a h squared of n. So that is sigma e squared into summation k equal to 0 to alpha a squared a power 2 pi. So that is a sigma e squared into 1 plus a squared plus a square a power 4 plus etc. up to infinity. So that is sigma e squared into 1 by 1 minus a squared. So 2 power minus 2b by 12 into 1 minus 1 divided by 1 minus a squared. So taking the z transform on both sides means we have y of z is equal to a z inverse into y of z plus x of z. So there is h of z is equal to y of z by x of z. So 1 by 1 minus a z inverse. So that is equal to z by z minus a. So h of z inverse is equal to z inverse by z inverse minus a. So we know that sigma e squared is equal to sigma e squared into 1 by 2 pi f closed interval h of z inverse is z inverse into dz. So substituting h of z and h of z inverse values in the above equation, we will get h of sigma e squared is equal to sigma e squared into 1 by 2 pi f closed integral z by z minus a into z inverse by z inverse minus a z inverse into dz. So there is a sigma e squared is equal to sigma e squared into 1 by 2 pi f closed integral, there is z inverse by z minus a into z inverse minus a into dz. So when we are taking the residue values, we will substitute the values. So that is the final answer will be z minus a sigma e squared into z minus a into z inverse by z minus a into z inverse minus a up to z is equal to 0 a. So there is a sigma e squared into a inverse by a inverse minus a, that is sigma e squared into 1 by 1 minus a squared. Next question is, the output of the analog to digital converter is applied to the digital filter with the system function of h of z is equal to 0.4 z by z power minus 0.7. So find the output noise power of the digital filter when the input signal is quantized to 7 bits. So that is h of z is given 0.4 z power minus 5 minus 0.7. So that is h of z into h of z inverse into z inverse is equal to, we have to multiply 0.45 z by z minus 0.72 into 0.45 z inverse by z inverse minus 0.72 into z inverse. When we are after multiplying, we will get a minus 0.2812 divided by z minus 0.72 into z minus 1.3889. So now the poles of h of z and h of z inverse are P1 value also get, P2 value also get. So the output noise power due to the input quantization is sigma E naught squared is equal to sigma E squared into 1 by 2 pi f closed integral h of z inverse into dz. So that is sigma E squared summation I is equal to 1 to n residue of h of z inverse that is z equal to pi. So that is equal to sigma E squared into summation I equal to 1 to n residue of h of z inverse that is z equal to pi. So p1, p2 etc. up to pn are the poles of h of z inverse that lies in the unit circle in z plane. So that is at last we will get the sigma E squared value as 0.420 into 90 squared. Next question is, consider the transfer function h of z that is equal to h1 of z into h2 of z, where h1 of z is 1 by 1 minus a1 is the inverse and h2 of z is 1 by 1 minus a2 is the inverse. So find the output round of noise power. We have to assume that a1 is equal to 0.5 and a2 is equal to 0.6. Find the output round of noise power. So the round of noise model is h of z is equal to h1 of z into h2 of z. So already you have given h of z is equal to 1 by 1 minus a1 is z inverse into 1 minus a2 is z inverse. So whereas the noise transfer function is e2 of n. So h2 of z is equal to 1 by 1 minus a2 is z inverse. So the total steady state noise variance will be sigma naught squared is equal to sigma naught 1 squared plus sigma naught 2 squared. So first we have to find out the sigma naught 1 squared. So that is 1 by 2 pi f closed integral is h of z inverse z inverse into ds. So that is sigma E squared into 1 by 2 pi f closed integral 1 by 1 minus a1 is z inverse, 1 by 1 minus a2 is z inverse, 1 by 1 minus a1 is z inverse, 1 by 1 minus a2 is z inverse, the z inverse into dz. So it should be said as sigma E square into summation of a residue of h of z inverse at the poles z is equal to a1, z equal to a2 and z equal to 1 by a1 and z equal to 1 by a2. So if a1 and a2 are less than the poles, z equal to 1 by a1 and 1 by a2 are lies in the outside the circle. So modulus z is equal to 1. So the residue of h of z is h of z inverse at z is equal to 1 by a1 and z equal to 1 by a2 are 0. So let me get the output of the value as sigma naught 1 squared is equal to sigma E squared into a1 by a1 minus a2 into 1 by 1 minus a1 squared into 1 by 1 minus a1 a2 plus a2 by a2 plus minus a1 into 1 by 1 minus a2 squared into 1 by 1 minus a1 a2. So in the same way, sigma naught 2 squared also we have to find out the same way. So let me get the output of the sigma naught 2 squared as a sigma E squared into 1 by 1 minus a2 squared. So after substituting the sigma naught squared, we will get 1 by 1 minus a2 squared plus a1 by a1 minus a2 into 1 by 1 minus a1 squared into 1 by 1 minus a1 a2 plus a2 by a2 minus a1 into 1 by 1 minus a2 square into 1 by 1 minus a1 a2. After that finalize we will get the output as 2 to the power of minus 2b by 12. So into 1 by 1 minus a2 squared plus 1 plus a1 a2 divided by 1 minus a1 squared into 1 minus a2 squared into 1 minus a1 a2. So the steady state noise power will be a1 is equal to 0.5 and a2 is equal to 0.6. Substituting these values in the above equation, we will get the output as 2 to the power of 2b by 112 to 5.431b. 5. Okay, this will be the output answer. Next, draw the quantization noise model for the second order system, that is h of z is equal to 1 divided by 1 minus 2r cos theta inverse plus r squared z inverse, and find the steady state output noise variance. So that is h of z is given. Then the quantization noise model is, we know that sigma naught squared is equal to sigma naught 1 squared plus sigma naught 2 squared. So both the noise sources sees the same transfer function. H of z is equal to, this value is given, and the impulse response of the transfer function is given by h of n is equal to r power n s sin n plus 1 into theta by sin theta into u of n. So now the steady state output is sigma naught squared is equal to sigma naught 1 squared plus sigma naught 2.